Okay, hey guys. Today let's continue on our peer tutoring session, which is our second session. And for this session, we'll talk about mostly still dynamics, but we will touch on we will touch all of the mechanics material, the dynamics material. So I think from watching the first and second session, you guys will already be set it up for the quiz one. Okay, so now we'll talk a little bit about it's circular motion. So when we talk about circular motion, we'll talk mostly on um, angular velocity, and after that we also have angular acceleration, which will talk mostly further on the rotational dynamics, but now we'll just touch on that a little. So angular velocity will take it as omega, and for the angular acceleration is alpha. So for the circular motion, mostly the question will be on dynamics part. So for dynamics part, for the dynamics, what I mean by dynamics is that it's involving all of the forces. It's going to be circular motion. It's any circular motion, and it has some kind of radius of the motion, and it's moving with the angular velocity of omega around this axis, obviously. So maybe the picture is a bit weird. I'll just draw it like this. It's omega. Okay. And for this kind of questions, you will just have to do this. You just have to put the normal Newtonian's equation, which is the sum of force equals to mass times acceleration. And the acceleration we're going to use is centripetal acceleration, AC, which is omega squared times the r, the radius of the circular motion, and that's it. So this kind of question will have some kind of variation. So mostly the variation will be on the forces and the radius, but other than that, it's just gonna be very easy to work on. Let's just try on our first question. Wait up. This is our first question. So if you have a bead of mass m suspended from one arm of a Y-shaped pole shown in the figure 2, and the pole is rotating around a vertical axis with an angular velocity omega, and the bead maintains a distance h from the center of the pole, derive the expression of omega. So, okay, it's really easy. Because the questions already told us that we should ignore the friction for this question. So what does they mean by the friction? Because the bead can move along this axis, along this pole, right? So because it can move either going further or going closer to the center of the motion, it can only move to this direction. So the friction will be going on either this direction or that direction. But because they ignore the friction, the only force that can be present here is only in this direction, on the perpendicular direction of the friction itself. Yeah. So as I told you earlier from the first session, and I want to highlight it again, is that when you draw a theta or any kind of angle, don't draw it close to 45 degree because it will confuse you. And this one is close to 45 degree, as you can see that it's almost like 90 degree, right? So it's almost like a 45-degree angle, and it's very hard to see. So my advice to you is to draw it either very small or either very big. For the past tutoring session, I tried using the very small angle, and for this session, let's try on using the very big angle. Okay, like this. So this angle is very big. Theta, right? So this is the bead, and the bead has weight, of course, which is mg, and it has a normal force. It can go either here or this direction. Either way, it's going to be okay to choose any, because if you got it wrong, if your assumption is wrong, the value of the normal force will be negative. So whatever. So we can see. So the first thing when you see circular motion is that you have to define where the circular motion is. What do I mean by defining it? Is that where does this point rotating to? It's rotating to this axis. So it's not, so the radius of the motion is not this, but it's this. How come? Because if you imagine, it's rotating this way. It's rotating this according to this. So if you see from the top view here, it will be rotating um, with the radius of this much, which will do this as the r, the radius of the motion. Because it's, so I'll draw the motion, draw the circular motion like this. Yeah. So now it's easy to see that because this is h, this is h, so r is obviously h sine theta. Okay. So as I told you guys, that the sum of the forces, so this sum of forces here is radial forces. Radial forces, and the notation is that plus is going to the center of circular motion. So positive forces is going to the center of the circular motion, which is, on this case, it's here, the circular motion. But we have n, it's not, it's going like a little bit shifted here. So you have to project those forces, these n forces. So you can easily see that because this big theta is here, so you have two angles, and the other one is this one, which is a bigger theta, right? So it is pretty obvious that this angle is theta. So it actually, if you want to track it on the correct manner, this is theta, this is theta also. Of course, this is 90-degree minus theta. So this is theta. But sometimes it's just easier if you draw the theta on a manner that it's very big or it's very small, on an extreme condition. So if you project the theta to the center of the circular motion, it's gonna be n cos theta. This is the sigma fr, because it's going to the middle, to the center of the motion. It is positive, equals to m times the centripetal force, centripetal acceleration, which is m times omega squared times r. This is our first equation. For the next equation is going to be on the other axis, which is on the vertical axis. We have the sigma force on the vertical axis going to be 0. Why? Because it's not moving on this axis. It's not moving up or down, right? Because it's not moving up and down, we have n sine theta, because if you project n to the vertical axis, it's going to be n sine theta, negative mg equals to be 0. So m sine theta equals to mg. This is the second equation. So if we divide second equation by first equation, it's going to be m cos theta over m sine theta equals to mg over m omega squared r. We can cancel out the m and n. Wait, sorry, it's sine over cos. Sine. This is cosine. So tan theta is going to be g over omega squared r. So the omega squared equals to g over r tangent theta. Wait, is it correct? Yeah, it is correct. And sine theta equals to mg. So yeah, tan theta is g over omega squared r. Yes. Okay, so it's done. So we're done with omega equals to root of g over r tangent theta. Yeah. I think that's it for this question. So also to recap the methods that I told you guys about from the first session. So to work on, because circular motion is part of dynamics, it's part of the mechanics. To work on it is that firstly you have to draw the free body diagram. So this is the free body diagram. You have to set up the equations. After you set up the equations, you solve the equations. It's still the same 1, 2, 3 steps I as I told you in the beginning of the session, on the first session. Sorry. So yeah, this is how you do the circular motion. This is the first example. We'll try on the other example. Yeah. Okay, before we touch on that, we'll touch on the other material first, because for the next question we have to understand some basic energy and momentum. So next up, we'll have to study more. Wait, before we go to the next, I'd like to tell you guys about another method that we will do on that can be used to understand force easier. So we'll touch on this fictitious force. What is fictitious force? So this is not so there will be no lecture or no materials on this fictitious force on PH1011, but because it's physics, I mean, you can always use another method to solve a problem. And this method is somewhat easier to understand for some case lah. So what this fictitious force mean is that if you are inside of a reference moving with an acceleration, you will see a fictitious force. U or you. What do I mean by you here is that is some subject that is also moving together with the reference. So it is very hard to word out, and I don't even know if this is called fictitious force, but as I learned it back in Indo, and people call it Gaya fictive, which is directly translated to fictitious force. So I don't know what it is called, but I'll just call it fictitious force. And it sounds cool, right? It's fictitious. It's like a ghost, right? So basically, if you are moving in the, let's say you are kidnapped in a truck, right? You cannot see that this truck is moving. There's no window, okay? So if this truck is accelerating A toward this direction, I mean by means accelerating is that. So the truck driver is gassing he's pumping the gas, so it's moving faster and faster. For example, if it's from stationary, from it's at first it's stationary and it's moving, of course you get, so it's basic lah. If you're in the bus, so the bus is not moving and suddenly it's moving, you get you get some kind of force backwards, like you feel that you are pushed backwards by some kind of force, which you obviously experience either from moving in MRT, bus, or a car or anything. So if it's from the initial condition with no velocity and suddenly it's moved, so when the things start moving, you get pushed backwards. Okay, I mean it's common sense. You get it, right? But actually there is no force that is pushing you forward, right? So it's just it, I mean it's just like a friction force. So if you're standing, there will be a friction force. But if you're sitting, there will be a normal force from your seat. But let's just imagine that you're standing because it's easier to understand. So from the Newton's second law, if you are an observer outside of this, if you're an observer outside this reference, outside this truck, right? I mean, even if the observer cannot see you, but if the observer can imagine that you are there, the observer will say that the sum of the forces equals to the mass times the acceleration of this truck, right? So the only force that you as a person here experience from the outside is F equals to ma. Why a? Why you're because from the outside, right, you're moving with the acceleration a, as well as the truck is moving with the acceleration a, because you're moving with the truck. Of course you have the same acceleration as the truck is. Okay, this is the first equation. I mean, this is not the first equation, this is just the equation of the motion from the outside observer. But if you are an observer also inside of this truck, right? So you're observer here, you're inside of the truck together with this person, right? So you'll say that, okay, because you're inside of the truck, you can obviously see him that is not moving, right? He's just there, he's not moving anywhere, he has no acceleration compared to you. I mean, with your reference here. Okay, so you say that, okay, the sigma force is zero. It is zero. How come that from your, and actually from this observer, he will also see that this foot of him will touch on the ground and have friction, right? So is it that from your reference that F equals to zero, but from outside observer it's F equals to ma? What's the correct one? Is it zero or ma, right? The thing is that if you are moving with the truck, right? If you're moving with the truck, you see a fictitious force. You will see a fictitious force. And this person will actually not only see but experience the fictitious force. Because I mean, because you are also a person here, you will also experience it. But you will see one. You'll see a fictitious force. So I'll just draw the fictitious force in red. The fictitious force. So before that, I'll just say that fictitious force will have the formula. So F fictitious, we will use FF here as the mass of the object that experience the fictitious force times the acceleration of the reference, acceleration of the truck on this case, because the truck is moving in this case. So M is mass of the object that experience it, and This is the expression variation of the reference. Okay, it's very hard to read, whatever. And its direction is, so the direction is directed to the opposite the opposite direction of the moving reference. Or basically it's just opposing the opposing the expression. So the Fictitious force from this is that is moving because the truck is moving rightwards. The Fictitious force is going leftwards. Okay, this is the Fictitious force. This is the Fictitious force with the with the formulation as m, which is the mass of this person inside, because he's the one experiencing the force. So m is the mass of the object that experiences the force, the Fictitious force, and the a is the expression of the moving reference, because this is the moving reference, right? So ff, so you have, it's not 0, this is incorrect, but you have the sum of the forces equals to 0, yes, but you have a fictitious force, negative the friction force, and the fictitious force is ma minus f equals to 0. So ma will still be the same as if you're observing it outside of this reference. So it's going to be the same, right? It's consistent. It's physics. Okay. So that's what fictitious force is. It will be useful on some cases. So firstly, I'll do this problem using the fictitious force first. How come? Let's just see. Okay, I'll just copy this, right? I'll just copy this free body diagram. Let's copy this page. Okay, I'll leave it at this. Okay, so because I already copied this, so if you're moving together with this particle, with this bit, moving with this circular motion together with this particle, because you have an acceleration to the center of the motion, right? You obviously have the Fictitious force opposing that direction, because the direction of the acceleration is this way to the center. The Fictitious force is going outwards of the radial direction, which is here. Okay, it's very easy to understand. It's the Fictitious force. Okay, so it is easier to do it this way. Okay, so we'll continue drawing the path of the bits. So this is the pole, right? This is the pole. So if you have this Fictitious force, you can see that, wait, you can see that this bit is not moving to either this direction of the pole, right? So you can just ignore the n, because the n is only there to the n is only there to counter the mg and the Fictitious force. I mean, because the mg and the Fictitious force have this projection to this direction, the n is there to only counter this Fictitious force and this mg. But the only way that this bit is on the stable condition, is not moving, is that the projection of this mg to this direction, to the pole, and is equals to the projection of the fictitious force to the pole also, because it's opposing each other, right? So it has to be the same. Okay, so let's get back to the drawing. This is theta, this is theta, basically. I mean, this is the big angle, and this is also the big angle, theta. So it is easily to be found that the FF sine theta equals to mg cos theta. And because the FF is obviously m times a, the m is, so we get back to the fictitious force definition, is that its mass is the mass of the thing or the object that experiences the fictitious force, which is here it's the bead, so it has this mass m. The acceleration is the acceleration of the reference, which is this reference is moving with circular motion, so the acceleration is centripetal acceleration. Sine theta equals to mg cos theta. You can just cancel out the m, so the acceleration of the centripetal acceleration is omega squared r. So the r here is, wait, we haven't finished this actually, because of what? Because the r here is h sine theta. So wait, r here, r is h sine theta, thus the omega is g over r sine theta tangent theta. Okay, let's continue on this. Omega r squared r sine theta equals to g cos theta. So we'll have that omega squared r is h sine theta. Sine theta, we just divide both of these by cos theta, and you have tangent theta equals to g. Thus, we have that omega squared equals to g over h sine theta tangent theta. So the omega here equals to the square root of g over h sine theta tangent theta. And it's the same as if we did it on the normal way, on the regular way of doing it. But it's shorter to do it this way, other than this way, because from this way, if you're seeing or if you're observing from outside direction, you can only do this on two axes, because if you want to apply centripetal forces, you can only direct it to the center of the motion. Okay, that's why it's longer. But if you're using fictitious force, you don't have an acceleration, you have a force, right? I mean, the acceleration here, it is translated into the fictitious force that is moving to the other direction. So because it's only force and it's not acceleration, you don't need to write sigma f equals to ma. You can write sigma f equals to 0 to any direction. Thus, any direction, we can use this direction, which is the easiest direction when you do this kind of question, because the reason that I told you earlier before. Okay, so yeah, oh, this is not R again, this is H. So sorry guys. Okay, so yeah, that's how you apply fictitious force. We'll touch on another kind of questions from fictitious force. This is actually I don't keep the problem. Maybe you guys check on it, but I think they have this kind of problem on my quiz. I still remember the problem because even before the quiz, I already did this question, because this is actually a question from International Physics Olympiad on the old kind of years. It's maybe like 19 something. This is M. It's either which one is M1 and which one is M2. I don't remember. Whatever. I don't really care. But the thing is that for this kind of question, there's a minimum force here. There's a force here that has to be applied to this kind of system, so that M1 and M2 is not moving relatively to this big M. What does it mean is that, so if you push this system, actually with these pulleys here, M1 should have moved and M2 should have moved downwards, and M1 should have moved rightwards, because there is no friction. So this force is telling us that there is no friction anywhere. Friction anywhere. Okay, so if there's no friction anywhere, there gotta be no problem, right? So the M2 will go straight away downwards and M1 will go rightwards. But because there is F here, so the system will be moving rightwards. Okay, the system will move rightwards with an acceleration. So if you still cannot see why, if you have an acceleration and there is no friction, that this thing will cannot move, is that because it's very hard to imagine. So just imagine that this is a car, and in front of your car there will be a pulley, and this will be an M. So there must be a way that if you're moving, these these two particles will not move somewhere or anywhere. I mean, it's pretty hard to imagine, right? From our observation, it's pretty hard to imagine. But if you imagine this from the point of view of fictitious force, it's gonna be easier for you to imagine. I mean, for the calculation, it's gonna be pretty similar. There will be not so much kind of difference here, but it's easier for you to imagine from fictitious force point of view perspective. Why? Because of course there's F here. There will be acceleration rightwards. When there will be acceleration rightwards, this M1 and M2 will only move with the reference to this big M, right? Because of that, you can see that because it's moving rightwards with acceleration A, both M1 and M2 will experience an fictitious force moving this direction to this direction. There's a fictitious force F here. Okay, it's easily understood because there's FF here. It will counteract this tension force, so it can balance out. Easy to understand, right? That's the way you see it from the fictitious force. How do you see it from, or what do you see it from fictitious force? I mean, how come you can see it from fictitious force? Is that you're moving together with this system. So maybe that, just imagine that this block is see through, and you're inside of this box and you see it, oh, this M2 and M1 is not moving. So obviously from your point of view, they both have the fictitious force here. Okay, easy to understand. So now, as I said it on the first session, for this kind of question, you just have to draw the free body diagram first. So if you have these three system, I mean this three object system, you have to draw it one by one. I mean, you don't have to, because if you see this system as a whole, system, you can say that because they're not moving to one another, relatively to one another, you have a system, one object system which has the mass of m1 plus m2 plus big M. If you times it by A, it's equals to the sigma force, and the sigma force for this three system is only F. So you have F equals to M1 plus M2 plus big M equals to A, and A equals to F over M1 plus M2 plus M. Okay, it's easier to do this, but sometimes you don't think about, you don't get it at the first time you see it. So you have to break it down for each masses. So for each masses, M1 will have this this normal force from M. I mean, it doesn't matter, the normal forces doesn't actually matter, but we'll just draw it. Normal force we have, let's just say N1. We have M1G, we have tension here, and because we're seeing this from the from the reference of moving system, we have to say that he has a Fictitious force, which is the magnitude of the Fictitious force is m1 times the acceleration of the system. Okay, so for m2, it's gonna be the same. The pulley, the tension is dragging it upwards. We have m2g here. We have also the normal force from the m, which is n2, let's say. I think that's it. Oh, and we have the Fictitious force, which is m2a. Okay. And for m1, we can also do the same. For the big M, we can also do the same. So big M experience n1 from here, n2 from here, f from here, and mg, and we have another normal force from the ground, let's say k. I don't know why I write k. I mean, doesn't matter actually. And as I said, can also write it as Fictitious force ma. Right, there's nothing wrong with this because we're seeing it from this perspective of Fictitious force. We will just say that sigma f is 0 to everywhere. Okay, so maybe from the m1 we'll just see the horizontal, which is t, the sigma f1 horizontally, sigma f1x equals to 0, t equals to m1a, because m1a is moving leftwards, it's dragging leftwards, and t is dragging rightwards. It has to be the same, right? Sigma f2x equals to 0, n2 equals to m2a, and sigma f2y equals to 0. So t equals to m2g. I mean, it's easy to see that n2 here has to be the same with this m2a, and t has to be the same with m2g. Okay, fair enough. So actually from with this and these two, we can already solve this by just saying it. Okay, we have that. Wait up. Oh wait, this free body diagram is incomplete because we haven't drawn the pulley. The pulley is in position of the big M. Okay, so the big M is dragged by this T there and this T downwards. Don't forget about this. Most of the students forget about this and they got it wrong. From my experience. So yeah, just draw this big M as as on the right, on the horizontal axis, we'll have that MA F is going rightward. What else? Oh, it's only F that going rightward, equals to MA plus N2 plus T. Why? Because going leftwards, we have N2, T here, and MA, big MA. Okay. So if you plug in that F equals to MA plus N2, N2 here is M2A, right? M2A plus the T here is M1A plus M1A, you have that A equals to F over M1 plus M2 plus M. It's exactly the same here, right? So it doesn't matter which one you choose. But yeah, if you can see this at the first time you see the system, it's very good. It cuts down a lot of time. Because the next thing you'll do is that you'll just equate this P equals to M1A and P equals to M2G. So if you will have M1A equals to M2G, so obviously A equals to M2G over M1. So you'll just equate MA here with this equation. you'll get the F already. So M2G over M1 equals to F over M1 plus M2 plus big M. So you'll have F equals to M1 M2 M M2G over M1. It's done. Yeah, this is how you do it. And exactly, this is, I think, if I'm not mistaken, the exact problem on the quiz is also with this format with no numbers. It's all on the variables of M1, M2, M and G. Yeah, exactly. So yeah, that's how you do it. Next, we understand enough about the dynamics, about the translational dynamics. By I mean translational dynamics, that it's only the dimension of your moving is only sliding, moving, or moving on kind of direction, but we haven't touched on the rotational one. I mean, even though we have rotational dynamics still is not enough to be called as rotational dynamics. Not yeah, circular motion is not enough to be called as the rotational dynamics, and we'll touch on that later on after we learn a lot of things related to momentum and energy. Momentum and energy. So in physics, we'll have a thing called momentum and energy. Wait up. Okay, sorry, I'll continue. So for this momentum and energy, it's a quantity that, yeah, that is important in physics. You have to understand this. But for this course, you'll get mostly the momentum and energy only in classical physics. So the energy will be mechanical energy, and as well as the momentum will also be only in mechanical. So the energy is the potential energy added by the kinetic energy. What is potential energy and kinetic energy? Potential energy, okay, potential energy can be on this course, yeah, only on this course. It can only be the potential energy due to the position. I mean the position due to the height. I mean potential energy always due to the position, but let's say first one due to height, which is the PE equals to mgh, and you have the potential energy due to spring extension. It's PE equals to half of K of the delta x squared. I mean, it's not only extension, it can also be contraction or whatever, but the delta x is the changes on the spring length, and I think that's it. And for the kinetic energy, it can be two also. It can be translational, which is half of mv squared, and it can be rotational. But we'll not touch on rotational kinetic energy for now because, yeah, as I said, I haven't explained about the moment of inertia, so we'll touch on that later. But I'll just write down the equation of half of I omega squared. Okay, and I think that's it for the energy. So most of the questions on energy will be dealt on mostly the conservation of energy. Conservation of energy, mostly on the quiz and the exam, yeah, will be on conservation of energy, which is E1 plus E1 equals to E2. Yeah, I think that's it. There is another kind of questions which we will deal with. is that if you have a work done, usually work done is when your energy doesn't does not conserve usually. So it's sometimes if you have friction or outside force, outside or external force. External force is just force. I mean, I'll just say this as force other than gravitational force. Yeah, then you have a work done. So the work done is W equals to the integration of F times ds, or basically it's just force times the distance, but the force and the distance have to be parallel. Parallel force and distance. I think that's it for the material. We'll touch on the questions example, but I think the questions. Okay. We'll touch on the question example. As I told you, it was related to rotational motion, right? And it's quite fun because at first you wouldn't have think about it. I mean, you wouldn't have get it at the first time you see this question. Okay, wait, no, not this one. You don't have to get it at the first time you do this. I mean, if you're very exceptionally smart, you might. But yeah. So the circular frictionless track of radius r is set vertically. It's just like this, and then this mass is thrown downward with initial speed v. So derive an expression for the minimum speed of the point mass at the top of the circular track. So what does it mean by? Do you have an expression for the minimum speed? Oh, okay. So um so this question is basically saying, wait, let me check if there is another subpart. Oh, expression for the minimum speed for the point mass to complete the circular motion. Okay, at the bottom of the track. The point mass at the bottom of the track. Okay. Okay. I get it. Again, so yeah, you don't have to thought about the solution when you don't know how does this works. Is that first we have to derive a minimum speed so that this mass, when it's thrown, it can reach this top point. How do you reach this top point? Is that okay? So it's only energy. So you have an energy here, which is both potential energy and kinetical energy. So before I start on potential energy, for the potential energy due to potential energy due to weight, due to height, I mean height. Your reference point can be anywhere. Because because the PE does not matter, but the change of the PE does. Okay. So if your reference point is here, at the first time, initially it will have no height because it's exactly on the reference point. So you'll just say that the PE initially is 0. Okay, so let's just take this as reference point. Why not, right? I mean, if you use this as a reference point, your potential energy is going to be mg times the height. This point to this point, the height is r. Okay, and at the top it's going to be 2r. So the difference, the change in the PE is from mgr to 2mgr, which is mgr, right? The change from here to this is it's added by 2mg, added by mgr. Mgr added by mgr is going to be 2mgr. Okay, but if you use this as a reference point, initially it's 0. It becomes, from this reference, it will have the IR, MGR. So 0 to MGR, you just add it by MGR. So the difference, the change in potential energy is going to be the same regardless the point of reference that you choose. So just choose as comfortably as you can. I mean, just choose anywhere that you feel comfortable with. Okay, but obviously don't choose some kind of dumb reference points. Like example, if you want to use this as a reference point, it's not going to be any help. It's going to be harder for you. Yeah, just choose some points that are comfortable to deal with for you lah. Yeah, whatever. So because this is the reference point, you have initially there will only be half of mv squared. Why? Because there will be no potential energy with this reference, equals to, at the top you don't need to have any speed, right? You don't have to have any velocity on top, as long as you reach this either way. If this at this point it has no velocity, it will just fall down, right? Yeah, whatever, you just want it to reach the top, right? You don't need it to have a velocity to complete the motion. You just need it to be on top. So on top, you just assume that the velocity is 0, but it's just stop there. Okay, when it stopped there, there will only be the PE, the potential energy, which is mgr. So easily the v squared equals to the square root of 2gr. This is for part A. Part B is the minimum speed. If you want to complete one circular motion, how to do that, how to complete one circular motion is that at any points of this motion, it will always have to touch the track. Yeah, obviously it has to touch the track, right? Because initially for the part A, right, for this time they have no velocity, so obviously it will just fall down, right? After it reaches the top, so it's going to move like this. It reaches the top, it will just fall down. It can fall on this way or that way or any way. It just fall down, right? But for the B part, you have to complete one circle motion. Every part of this motion will have to have a certain value of normal force with the track. Why normal force? Because the normal force is the indication of the touching. So if you have a normal force with your particle with your track have a normal force, then there will be touching. It will touch, but if the normal force is 0 or less, I mean, there will be no less. There's no less than 0 normal force. But if your normal force is 0, then there will be no normal force, or we can just say that it's not touching the track. So you have to touch the track. Have to touch. When you have to touch the track, you have to have a non-zero normal force normal reaction force if you want to make it complete, but this is normal force, whatever. So the most extreme condition is obviously on top, right? Because like on top, it's the biggest possibility when it falls down, right? And so obviously we just take the top as the point lah, as the extreme point. So on the top, right, there it has to still have the normal force. So because this is a circular motion, with this point as a radius of the motion, we'll just say that okay, normal force. We'll do the centripetal thing. Sigma F equals to m times a centripetal. The sigma force here, they have both normal force and gravitational force. So N added by mg equals to m added by ac. AC here has to be what? Has to be v squared over r, or omega squared r. But whatever, because I haven't give you the relation. Okay, omega equals to v over r. This is the rotational logics. If you want, yeah, this is important. I didn't write it, sorry. So AC can also be represented as v squared over r. Because if you plug in this omega to this, it will come out as this v squared over r. Yeah, sorry. Thus the n is mv squared over r plus mg, negative mg, sorry. And it has to be non-zero, and it cannot be negative. There's no negative normal force, because if you have negative normal force, your normal force going this way, you cannot have that. I mean, when you touch the, if that's the case, when you touch the wall, the wall might pull you to the direction of the wall, like pull you into the wall, and it doesn't make sense, right? So yeah, that's why. So it has to be bigger than 0. Thus, we'll have mv squared over r equals to larger than mg, so v squared has to be larger than gr. This is the condition on top. So the velocity on top, on the most top of this track, has to be bigger than gr. Okay. So let's just continue with our energy. So based on reference point, we have the initial energy gonna be the same, half of mv squared, with our same reference point. Okay, half of mv squared equals to mgr, but on top now, your velocity has to be bigger than something, right? So obviously you cannot have a zero kinetical energy on top, but it has to be added by the top kinetical energy, half of mv top squared. So I'll just write this v squared as v top. So we can continue on cancelling out m times all of this by 2. We have v squared negative 2gr equals to v top squared, right? Because v top squared has to be larger than gr, so v squared minus 2gr has to be larger than gr, right? Wait up, is it correct? Yeah, it's correct. So v squared has to be larger than 3gr. Okay, that's it. Wait, is it correct? don't think why does it seem like there's something missing. Half of mv squared mgr. No, it's correct. Yeah, it is. Yeah, this is how you do it. So you just substitute phi top here by phi squared or minus 2gr. So phi squared minus 2gr is larger than gr. So phi squared has to be larger than gr. Notice that phi here is the velocity here, not on this top, because on this top I represented it as the phi top square. So I'll just write here this as v, and this is as v top. Okay, that's how you do this question. And let's see what the C question is. Do you have an expression for normal contact force on point of mass at the bottom of the track? So I don't know for this C question. Is it a continuation of the A or B? But let's just do for both, right? I mean, we don't need to know actually. I mean, yeah, we don't need to know. So sorry. So if you have V here, and this is the track, and this is the bottom right. So I'll just continue this as my reference point, whatever. At time 0, it's half of mv squared at this point. And at the bottom point, the PE will be, because the height is negative r now, it will be negative mgr added by half of m phi bottom squared. I'll just say that phi here is phi bottom. Okay, this is phi bottom. So it will have an m here, have an mg downward. So we'll have a phi bottom. So we can just cancel out the m and just times out it by 2. Phi bottom squared. It's going to be phi squared added by 2gr. Yeah, if you continue the math here, it will give out this. Okay, and n minus mg, it's the force, the sum of the force to this point, because the center of the circular motion is here. The sum of the radial force to the center, it has to be equals to m phi bottom squared over r. So n equals to mg added by m phi bottom squared over r. We just substitute this equation 1 to equation 2. We'll have that n equals to mg added by m over r. It's phi squared equals to gr. Yeah, it's going to be mg added by m phi squared over r added by 2mg. It's going to be 3mg added by m phi squared over r. Yep, that's how you do it. Yeah, I think that's it for this question. This is the C part. So it doesn't matter for A and C. It's going to be the same, because it's depending on V, and V here is dependent on the condition. If you want C part for the continuation as A, you just plug in phi. Oh, it's phi squared or squared of 2gr. No, phi is squared of 2gr. Here, yeah, it's correct. So it's phi. It has to be larger than squared of the 2gr if you want to do that. Yeah, just plug in any value of phi. Okay, that's how you do it. Okay, now we'll touch on momentum. So momentum will have the P equals to m times v. Yeah, m here is mass and v is velocity, and that's it for momentum. So for momentum, we'll mostly find the questions on the conservation of momentum. which is the initial sum of P is equals to the final sum of the P, or I mean just the sum of the momentum has to be constant with the um, condition of no external forces. So this is the condition for conservation of momentum. For conservation of energy, there's actually also a condition which is no external work done. Yeah. Oh, I haven't give you an example for this, but yeah, we'll try to do that later on. No external force, but if also as it is also in the momentum as on the energy, when you have no external work done, it's the energy is conserved. But if you have a work done, you have this, and also I have to continue this. Is that the work done is equal to the changes of the E. I mean, it's logic lah. If you have a initial energy and it's drained to be uh to be a friction work done, of course the final energy equals to the initial energy minus the work done. Okay, we'll touch on this on the other example later on. For that, so when, as I said, if the momentum is not conserved, you have an impulse. So the impulse is, let's just give this I equals to the change of momentum. Same as the work equals to the change of energy. And before we go into the questions, I'll have to teach you a little bit about the coefficient of restitution. Coefficient of restitution. What is coefficient of restitution? Coefficient restitution is E equals to the relative velocity after the collision. Usually it's collision or just after any kind of like any kind of collision or touching over the initial relative velocity. Here, this is the coefficient of restitution. So this is prime, meaning it's final relative velocity. It's initial relative velocity. So what do I mean? Oh, and the relative velocity on the touching point. So what does it mean is that so relative velocity is just relative velocity. If you have two things moving crossing into one another, their velocity going to be added one. Because when you see from this reference point, if you're moving with the velocity v1 and there's someone moving with velocity v2 closing into you, you'll see that that person is moving with the velocity v1 added by v2, because from your perspective you're always stationary. Like if you're in a car, yeah, you can imagine this. You're in a car and you're seeing outside of the road. You're moving forward, but the road is moving backward from your point of view. Why? Because from you, you're not moving. but because you're moving forward, the road is moving backwards with the same velocity as your movement. So that's basically the um, coefficients of restitution. We'll touch on this later on, but the thing is that when your E equals to 1, that means the collision is elastic. If it's not elastic, it will be less than 1, but it will always be bigger than 0 in non-elastic. But if E equals to 0, it's completely inelastic. So I don't think the prof taught us about this, but this is the funny story is that I use this because I learned this before in physics Olympiad, but I used this and the prof told me that I used this on the quiz, but the prof told me that my working is incorrect. So I asked the prof and I used a whole whiteboard to explain him about this coefficient of restitution, and in the end he accepted my answer and corrected my answer to be a full mark on that question. So yeah, I think now you can use that because the prof already know it from. I mean, it's not a good joke. Sometimes if you have different prof, I mean, because this method is very easy. I mean, it's very effective compared to the regular method of using the energy. But if you still want to use energy, it's on you. But most of the time, I'll use coefficient of restitution. Maybe for the first question, I'll try to do with energy. So yeah, let's just start with the first question. Okay, let's continue. Sorry, I have to charge my stylus battery. It's running low. Okay, yeah, this is the kind of questions of the momentum, and maybe we should have more questions on momentum and energy, but apparently we don't have that much time. So yeah, whatever. We just try to do as much as we can. Yeah. Um. So the bullet here has mass, and it's fired toward another mass, and it it moves the block here moves by some centimeters, yeah, by 5 centimeters actually. And the question is that the initial speed of the bullet. So yeah, for this kind of questions, it's not that we have to apply conservation of energy from the start, because the thing is that the bullet at first, so this problem has to be break down into two. The breakdown has to be break down into two parts, which is the part one is part of collision. The collision part is that the initial momentum of the bullet is mv, and because after the collision, both of the bullets and the blocks moving together with the same velocity, it's going to be m plus m v prime. Why? Because it's one thing. It's one entity. Yeah. So the final velocity is going to be mv over m plus m. Okay. And after that, we'll have the energy part. Energy part is where after the collision, the both of these things will both compress the spring. So before the initial energy is going to be half of m plus m, which is the embedded bullet into the block with embedded bullet times v prime squared, because it's after the collision, equals to um half of k delta x squared. Why we don't have the kinetic energy in the end? Because in the end, you want to have the maximum, the distance is the maximum distance. It moves by that much. Because it moves by that much, at the end of the movement, there will have to be stationary, right? There will be no kinetic energy. Thus, our can cancel out this t. So v squared equals to k delta x squared over m plus m. So the phi prime, because phi prime is this, we just substitute both two. We got that mv over m plus m squared equals to k delta x squared over m plus m. So m squared v squared m plus m squared equals to k delta x squared. So over m plus m, we just cancel this out. So v squared equals to k times m plus m delta x squared over m squared. So yeah, you get the initial velocity by just square rooting of these two and plugging in the information. Yeah, you know. Oh wait, no. Okay, this is the wait. So sorry. I'm so sorry, because the energy here does not conserve because they do have a friction. Okay, this is a great question. So sorry, this is a great question. So um imagine, so so because it's done already, we just say that imagine if there is no friction. So out of this question, there is no friction. Well, let's just say that I did this intentionally so that I can teach you about the conservation of energy. But now that the original questions will have to deal with the condition with the friction. So imagine if there is no friction, the answers would have been like this. Okay, and yeah, that's intentional so that I can teach you about energy, and then now I'll teach you about the work done. Okay, okay. So for the first part, still we still have to break it down, but the breakdown, the part one is still the same. The collision part is same. Part collision is exactly the same. Exactly the same. So still phi prime equals to m phi m plus m. But the energy part is different. Why? Because the energy does not conserve, but some of it is drained to the friction, to the work done by the friction. Okay, what does it mean? Does mean that, okay, because there's friction, so for this work done, I usually like to explain with the logics other than just plug it into formula and using negative value and stuff. The easiest thing is that because there's friction, there we have energy one and we have energy two. There is friction. What friction does? What friction do is that it's decreasing the energy because some of the energy is drained into the friction. So energy two is less than energy one. So some of the energy one is gone to the friction, right? So we can just say that energy 1 negative and energy 2 is the work done by the friction, right? So that's it. I mean, if you want to use this thing, you have that W equals to delta E. Delta E, obviously delta E is always final minus the initial. I mean, it's always that the final energy subtracted by the initial energy. But how come that our um our equation here is E1 minus E2. It's supposed to be E2 minus E1, right? I mean, because it's the difference in energy. Because actually, if you plug in this formula, you'll use the negative W because the force is going to the left. The friction force is going to the left. So it's E2 minus E1 equals to minus mg mu times S. But the W here is that in this case, I would just use that W is always positive because it's the logic. Right? The logic is saying that energy 1 has to be larger than energy 2. So energy 1 negative energy 2 is a positive number. It's a positive work done by the friction. So we're seeing it from the friction point of view. I mean, if you want to use the regular methods like this, it's good to do. But I mean, I just want to explain how does this work physically. So physically, half of m1 plus m v squared, v prime squared, negative. The energy 2 is half of k delta x squared. It's the same because energy 1 here is the kinetic energy and potential energy equals to the work done, which is the mg mu, which is the friction force, times the delta x here. So the phi prime squared. Oh, the m here is, sorry, it's m plus m. It's not m because it doesn't fit. Sorry. So the phi prime squared is wait, we should plug in. Sorry, it's pretty complicated there. We should plug in the phi prime equals to m phi over m plus m, and phi prime squared over 2, it's m squared m plus m, right? It's correct, right? Yeah, it's correct. Equals to half of k delta x squared. It's not phi prime again because we already plug in squared. Plus m plus m g mu times delta x, right? So the phi squared is going to be k delta x squared m plus big M over m squared added by m plus m wait, I'll just over m squared. It's times 2g mu delta x. Wait, is it correct? Yeah, it is correct. Yeah, and just plug in the value and then just square rooting this will do the work done. Will do the job. So I mean, obviously, if you square root this, because this thing is the same with this, but still added by the friction. What does it mean? It does mean that when you have a friction, you need to have a bigger v to reach the same distance of delta x, which is very logical because if you have friction, you need to have a bigger initial velocity because some of the initial energy is drained to the friction, which is, so this too is logical. Okay, so yeah, I think for now that's it. We'll do more on the rotational. It turns out that for this session, the transitional energy does not fit into this session, so we'll do it next time. So see you. Bye. Thank you.